All right, so now we're going to talk about the security of a crypto system. We've talked about a few different ciphers that we can use, but one of the big problems that people study in cryptology is how secure are these crypto systems? How secure are these ciphers that we use? And so the word that we use to talk about the study of the security and how to break crypto systems is cryptanalysis. All right, so this is a study of breaking crypto systems and studying the security of crypto systems. All right, so let's recall a crypto system is made out of two different parts. First is the encryption algorithm, and the second is the key. All right, so we're going to look at the security of both of these parts. So the algorithm is usually really large. Sometimes the algorithm is a mechanical device, the Enigma machine, for instance, in World War II. Sometimes it's an actual computer. You can kind of think of the football that the president carries around. Or oftentimes it's a mathematically complex procedure. But with all of these things, it is large and it is hard to keep secret. It's very hard for everyone who needs to know it, but everyone who don't want to know it to not know it. It's just too difficult and complex to really keep secret effectively, whereas the key is very small. Usually the key is 1 to 2 numbers. Right? And that's all there is to it. And so if you need to transfer the key between people, it's just a matter of getting 1 or 2 numbers across. The key can be transferred at any point. It doesn't need to be transferred with the message. It could be transferred weeks before the message. You can agree that on this date we will use this key. And so with all of this tells us that the key is easy to keep secret. And these two together give us Kirchhoff's principle. All right, and Kirchhoff's principle says that the security of a crypto system depends on the security of the key. Not the encryption algorithm. So you could have the most complex and complicated encryption algorithm in the world, but if the key is not secure, or in particular, if the key cannot be guessed at very easily or determined very easily, then if the key can be guessed and determined very easily, then your encryption algorithm will not be secure, because people can figure out the encryption algorithm. But if they can't get to the key, they can't use it. All right, and so this now leads us to, how do we break encryption? Okay. So let's say we are a hacker and we intercept the following ciphertext. All right, so we are somehow able to get our hands on an encrypted message. Let's say the message looks like this. UAYXIYMHINLYGUCHMYWLYN. All right, there are no spaces there. Remember, our alphabet is just the lowercase letters. This makes no sense. All right, we have no idea what this could possibly be saying. And so what we want to do is we want to be able to turn this into plain text. And assume that we know they used a shift cipher. All right, somehow we're able to get our hands on the encryption algorithm that was used, and we know that a shift cipher was used. But we don't know the key. All right, so our goal is we want to figure out what is the key that was used on this algorithm. Well, there's one obvious method for doing this. That's the method of exhaustion. We can just try all the keys. All right, there's only 26 keys because the shift cipher, all it does is it shifts the letters a certain amount over in the alphabet. Well, there's only 26 spaces to shift to until eventually you wrap around and just get back to your original letter. So there's only 26 keys in total. And one of those keys is not shifting at all. So really there's only 25 keys. So it's not very hard for us to simply try every single key and see if we get a message that makes sense. We're going to need a computer. This message is not terribly long, but if we had a message that was pages and pages long, you'd want a computer in order to do that. But this is a very simple algorithm program to write to decrypt this given a particular key. And this method works because there's only 25 keys. What if there were 10 trillion keys? And so we're going to look at more complex algorithms as we move along. The next algorithm that we're going to look at is going to have a little bit more than 300 keys. And already that's going to take an annoying amount of time. Not impossible by any means, but even with a computer, it's going to be annoying to try and use every single key in your arsenal. So the exhaustion method is a good one, but not really practical for real algorithms. Because you're going to have more than just 26 keys. This also brings up another point, which is worth noting. This hacking a message is made much easier when the message is from a natural language. All right, and what I mean by that is a language that we speak and read, because once we decrypt it, we know that we have the right key because it looks like an actual message. You can imagine a situation where it's credit card numbers, all right? And for credit card numbers, you might decrypt it and it still just looks like gobbledygook because you don't know if you have the right number. It's not really until you test it that you know that you have a valid credit card number. And of course, there's probably downsides to just testing random credit card numbers. You're going to flag some signals at the FBI eventually. So this is the downside of encrypting a natural language message, is that it's easier to decrypt. It's easier to hack into because it's very easy to tell when you have the right key just by the fact that gobbledygook turns into a piece of text that actually makes sense. You know you've got the plain text at that point. Okay, but that being the case, let's continue on and look at another method for hacking into a message. And so this method uses statistical analysis. All right, and this is actually really cool. This basically builds off of the idea that the letters in the English language do not appear with the same amount of frequency. So in the English language, certain letters appear more often than others. So for instance, someone has done a study on this and come up with a really nice table that shows the general frequency of each letter of the alphabet in the English language. All right, and this is American English. And so if you look at this table real quick, you can immediately see that E shows up way more than anything else. E is one of the most frequent letters to show up in the English language. Then we've got a few more. We've got A, we've got H and I, S and T, right? R shows up pretty frequently. N shows up pretty frequently. All right, and then you start going into the L's. O shows up pretty frequently. And then if you want to know the least frequent one, where you're talking about things like Z here and Q. All right, so we can use this fact to examine our ciphertext and try and figure out what each letter corresponds to. Because remember, all we have to do is figure out what one letter corresponds to, and that will tell us what our key is. So, as we saw, E seems to show up the most. So can we examine this ciphertext that we have up here and try and figure out, okay, what letter shows up the most in this ciphertext? Right, and this one, it's pretty easy. We see a lot of Y's showing up. All right, and in fact, someone has taken a look at this ciphertext right here, and turns out that Y definitely shows up the most, followed by M, N, and L. Okay? So Y seems to show up the most, and we know that E shows up the most in regular English language. So we can then make a guess. Oops. We could then make a guess that E gets encrypted to Y. All right, well, if E is being encrypted to Y, then we can take a guess as to what our key is going to be. So if we take a look over here, we see that E is being shifted 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 spaces over. So we could guess that our key is equal to 20. And so if we took a look at that, then we can look at some of the other frequent letters that show up in our message and see if they also correspond to frequent letters in the normal English language. So for instance, one of the frequent letters is M. All right, that's one of the most frequent ones after Y. So if we have a shift of 20, what gets encrypted into M? Well, it's going to be S. And let's see, another one is, let's see, I. Okay, I is another very frequent one. All right, so what gets encrypted to I with a key of 20? Well, O does. All right, and we can see that both S and O are very frequent letters. Okay, so this seems to make a lot of sense. So the last step is simply to plug this into a computer and shift each one of these letters 20 units the other direction to decrypt this ciphertext. And once we do that, we see that we in fact do get a natural message, which tells us that yes, our key should be 20. So this did not involve actually trying every single key, but instead looking at the most frequent letters that show up and say, okay, well, they probably correspond to some of the most frequent letters that show up in the English language. It doesn't always work with E. It depends on the message. Sometimes it'll be T or A or S. But it reduces the number of guesses that you have to take considerably down if you have a large number of keys. Now, this statistical analysis is not 100%, and it works best when you have a large number of, or a large message that you're working with, a large number of letters in your message that you can work with, because then the probability that you actually do have E showing up the most it gets higher and higher depending on as the message gets longer and longer. All right, so we will be using this method of breaking encryptions multiple times as we look at different ciphers. And we'll look at some more complicated ones as we look at more complicated ciphers.